And we're back in Better Than Ever, still in 18-1, where we're taking a look at reaction rates. In the last podcast, we reviewed the idea of a chemical reaction where reactant bonds must be broken first before product bonds can form. In order to do that, you must put energy into the system to break those reactant bonds, and the energy comes from the collision of reactant particles. That's the idea of the collision theory. So therefore, if you increase your concentration, you're going to get more collisions, more reactions, at a faster rate. Conversely, if you lower the concentrations, you'll get fewer collisions, fewer reactions, and a slower rate. But as it turns out, even if you calculate the number of collisions that are occurring, you're not going to be getting a reaction every single time two molecules collide. So let's take a look at graphically why this is. We're going to turn to the next page. I'm going to scroll down here. We're going to take a look at the difference between exo and endothermic reactions. We're going to label the y-axes with energy on both graphs, and we'll label the x-axes with reaction progress, which is basically time. All right, and we'll take a look at the exothermic reaction first. I'm going to go ahead and change colors here. Let's go to an orange color. And let's just say our reactant starts with a certain amount of energy. Let's just say right here. So we'll label this reactants. And we'll say that our products end with this amount of energy. All right. Now, in order to go from reactants to products, you're going to have to lose energy. Well, when you lose energy, energy is going out. That's why it's called exothermic. Exo meaning outside or to lose, and therm meaning heat. So this reaction is obviously losing heat because the products are lower in energy than the reactants. But as you go from reactants to products, you first must add energy into the system to break the reactant bonds before the new bonds form. And as the new bonds form, they will release the energy as they move towards product. All right. So, though there is a net loss, and that's what we'll put in for exothermic reactions, there is a net loss of energy. You initially have to put energy into the system before the energy can come back out when the new bonds form. Now when this happens, you're going to have a warm feeling when you put your hand up to it. So we'll just say that this feels warm to the touch. Now this amount of energy that must be added, I'm going to go ahead and switch up colors again. Let's go with, say, green here. The amount of energy that must be added from reactants to overcome that hump and to break the reactant bonds, this is what's called activation energy. And we give it a symbol E for energy, sub A for activation. So therefore, not every collision will have enough energy to overcome that activation energy. For example, when you try to crack an egg, you could gently tap that egg on the countertop and it won't crack the egg. You have to use enough force to actually break the shell. It's the same thing when you're breaking chemical bonds. Two molecules might collide, but they might not collide with enough force to actually break those reactant bonds, and if they don't, the product bonds cannot form. Now, if you take a look at an endothermic process, we could say, I'm switching over here to purple, we could have the reactants that have relatively low energy. The products will have higher energy. So overall, there is a net gain of energy as you go from reactants to products. Net gain of energy. And so when if this is gaining energy, if you put your hand up to it, it's going to take that energy from your hand. When energy leaves your hand, it's going to feel cold to the touch. But the actual pathway or energy diagram is going to look something like this. where you're going to have to put energy in to break the bonds, and then relatively little energy comes out. And so overall, you did put in more energy than came out, so that would be a net gain in energy. And once again, the difference between the reactant energy and the energy required to overcome the bonds is going to be the activation energy. In this case, there's just a relatively large amount of activation energy. And so every energy diagram is going to look something like this. It just depends on how big the hump is or how much activation energy is required. All right. So not all reactions will produce not all collisions will produce a reaction. Now the other thing that's interesting about this, let's go back to black here, is we have a name for the morph state that's caused when the reactants collide. Let's take a look as you look down the page. Here's a collision of particles. Here you actually have two nitrogen monoxides colliding with a bromine molecule, which is Br2. What actually happens when the molecules collide, which is right here, they will actually squeeze together to form this energetic state. You can almost think of it as when, say, a tennis ball collides with a racket, that tennis ball compresses, or when a golf ball hits a club, or a basketball bounces off the ground, etc. It always is kind of this squeezed, morphed, compressed state. And we have a special name for that in chemistry. We call it the activated complex, or we also will call it the transition state. It's an activated complex because it has extra energy above and beyond what the molecules normally have. And you can call it a transition state because you're transitioning between reactants and products. If there's enough energy in that transition state to break the bonds, the molecule will rearrange itself to form the products. If they collide and there's not enough energy to overcome those bonds, it will simply go back to reactants and they'll just bounce off one another. And so those are the two choices. Alright, so in terms of energy, the collisions must have enough energy to overcome the activation energy for this whole process to occur, or for this reaction to occur. When they collide together with sufficient energy, the activated complex forms, or that transition state forms, the molecule rearranges itself, and the new product bonds will form when they bounce off of one another. Depending on the amount of energy that must go in and come out of the reaction, that will determine whether or not the reaction is exothermic or releasing heat, or endothermic, which means it's gaining heat. In the next podcast, we're going to take a look at the effects of temperature on the rates of reaction. We'll see you next time.